Hi everybody, and welcome to the beginning of chapter 6. So we're going to talk about another form of graphing called the polar and the vector systems. So this fortunately is really a light intro into this, so hopefully you have a copy of the notes. Make sure that you get that, and as you're watching this video, make sure you start filling it in. So what we have been used to, as I'm looking at my notes right now, it's actually mismatched here. The rectangular system and the polar system, these should be flip-flopped. We've been doing the rectangular system since Algebra 1, right? If you remember the rectangular system, not the polar system, the rectangular system uses a coordinate system like x and y, and you're used to having the x-axis, the y-axis, and if we were graphing something like 3, -4, right, x tells me whether I'm going left or right, depending on positive, negative, and y tells me whether I'm going up or down, depending on negative, positive. So graphing the coordinate point 3, -4 would place me right here, right, and we use it because it's formed in a rectangle. Well, there's other ways that we can graph, and there's other purposes in which we might want to graph. This is used a lot of times for things that have straight lines going in up, down, left, and right. But not everything travels in straight lines. Some things travel elliptically or circularly. So something like that might be how a planet rotates the sun, or how a electron rotates a nucleus in an atom. So we might use something called the polar system because we have a pole in the middle and we have sort of a circular movement. And of course, we're going to use angles. Now, the way that we use a polar system is going to be similar to rectangular. It's two elements. The first one is r. I hope this makes sense that r would be radius because we're talking about circles. And the second one is theta, which would obviously be our angle. Now, the good news is most of this will be in degrees. We will occasionally see radians, but probably most of the polar systems will be in degrees. So if I was to graph something like the coordinate 2, 120 degrees, what we want to first think about is obviously where is the 120 degree mark. So we can see that right here. And each of these sort of red rings around represent a radius. So this radius is radius 1, this is radius 2, radius 3. So I basically think of it this way. I want to be on the second radius ring of my system, and I want to, from the standard position, rotate 120 degrees. So right here is the coordinate 2, 120 degrees. Okay? Now what's interesting about this system is that the center, just like the origin in the rectangular system, has a name, and this is called the pole. This is essentially when radius equals 0. Okay? So yeah, that is generally the idea of how the system works. Now, what we're going to have to deal with is different ways to express those. So, in example 1 here, we are given a polar coordinate, and we want to think about how I can graph it on my nice little coordinate plane over here. So let's start by graphing the coordinate 4 pi thirds. So this one is in radians. All right, so we have to be on the 4th radius ring. So starting from the pole, I go 1, 2, 3, 4 out, and I pivot to the pi over 3 angle, and I look at that intersection of that weird looking spider web like thing, and I call that coordinate A. Then I go to 2 and -3 pi over 4. Now, some of us might be really familiar with the -3 pi over 4 angle, and it's fine to keep it this way, but like every other system that we've been dealing with, we can add 2 pi to the angle and get the same coordinate, and I'll show you why that works this way. So if I add 2 pi, that gives me the coordinate 5 pi over 4. For my friends that are forgetting, that means we have to make a common denominator, so that's the same as 8 pi over 4. That's how I'm getting 5 pi. So I want to plot the coordinate point 2, 5 pi over 4. So again, I'm going to start at the second radius ring, and I'm going to pivot around the ring until I get to the coordinate 5 pi over 4, which is right there. I lost my place. There it is. Okay. Now, you didn't need to do that. If we think about 2 being my second radius ring. Oh, I graphed it the wrong spot. My bad. It's hard to see sometimes on these systems. So here I started 2, and I could just pivot in the negative 3 pi over 4 degree like that. So, you know, we do end up in the same direction either way. So whether you want to keep it as the positive or keep it as the negative or switch to positive, it will not matter for graphing purposes. Okay, so this is coordinate B. Now I'm hoping that you're looking at this next one and thinking, what is happening here? For the first time ever, we have an introduction to a negative radius. So we have the -1 radius and the pi angle. So you might think, well, one way that we can do this is instead of going in the positive x-axis, we actually just start at the negative x-axis. And that's actually true. We could start at 1 in the negative x-axis direction and pivot pi like that. So this would actually be the coordinate right here. The other way that a lot of people like to do it is pretend that it's not negative in the first place. Start at 1. So just ignore the fact that it's negative. Go pi around and then shoot back through the pole to the opposite side. So I basically am going around and back. That's another way to do it. Now, the other way that we can think about it is for negative radius specifically. So please make sure you add this for negative radius. If you add or subtract pi 180, you change the radius sign from positive to negative or vice versa. Okay, so in this case, if I add pi, I can rewrite the coordinate as +1, 2 pi. Or I could have subtracted pi, depending on my choice of why I might want to do this. So pi minus pi is 0, and I get 1, 0. So notice how all 3 of these coordinates, if I was to graph any of these 3 coordinates, would all place me back right where my first coordinate is. Personally, my choice is to add or subtract the pi to change the sign of the radius and then just graph it in the positive format. But if you decide to just do the angle and then go through the pole to the opposite side, that also works as well. Okay, so that's how we graph those. Now, one of the things that's kind of important is the fact that if you think about how these might work, I can graph a rectangular coordinate, but I can also kind of think of it in terms of its polar form. So let's look at an example here. If I wanted to graph the coordinate 3, 3, so let's do a quick sketch here in our notes. So let's say I have the coordinate 3, 3, 3, 3. So that's going to place it right here. But remember, the way that our shapes work here is that we have circular radii. So if I think about making this circle, I'm going to try to make it big so it kind of looks like that graph. If we think about it, right, I want to think about expanding my circle radiuses out all the way here. Now, it's not a radius of 3, because this would be 1, 2, 3, going out this way, 1, 2, 3. So it's a little bit bigger than 3. And so what tends to make more sense is instead of thinking about it in terms of the circle at first, rectangular systems have an x-coordinate and a y-coordinate. I hope you see what I'm doing here, because now I can make this into a triangle. And what's important here is that we know the angle of that triangle. This is a 3 by 3 triangle. It's a right isosceles triangle, so I hope you see this as a 45, 45, 90 triangle. So we know the angle of the 45, 45, 90. Now we just need to find the hypotenuse. Since this is a special right triangle, you might already see it as the ratio a root 2. Right, so the hypotenuse in this case is 3 root 2. And in a lot of cases, we're going to use Pythagorean theorem in this. So a squared plus b squared equals c squared, whichever you prefer. Obviously, if it's a special right, you can do this. If it's not a special right, you have to do Pythagorean theorem. So now we know the angle and the radius. So the radius of this circle would be 3 root 2, because that's what connects, it's a terrible circle, but that's what connects the actual length from the pole to the coordinate point, and then our angle here would be 45. Okay, now again, if you wanted to write this in pi over 4, that's fine, but you know, when we're drawing the triangle, we do it in degrees normally. Okay, so let's try another one here. So -4, 5. So if I was again to sketch this graph, -4 takes me 4 in the negative x-axis and 5 in the positive y. And if I form my right triangle here, unfortunately this is not a 3, 4, 5 triangle. So we can do Pythagorean theorem. So we go 4 squared plus 5 squared equals, I'm going to say r squared because that's really the radius of my overall circle in the polar format, right? So we get 16 plus 25 equals r squared equals 41. So the radius of this circle is square root of 41. Now, is that going to be a circle that we actually draw? No, but that's what the length of the radius would be. So the real question now comes in. If I know the radius, how do I find the angle? In the previous one, it was a special right triangle. We knew the angle. In this one, we do not know the actual triangle, so we have to use our calculator. And if you remember back from geometry, knowing any two sides of a triangle, particularly a right triangle, we can use the inverse tangent function or arctangent function. So if I do tan inverse of 5 over 4, that will get me the angle in the triangle, which, let me do it right here, 5 divided by 4 gets me about 51 degrees, 51.3 degrees. So that's the angle inside of here. Now, I'm hoping you're starting to think, but don't we always rotate from here? And the answer is yes. So even though the angle is 51.3, we need to find its supplementary angle, which means I have to do 180 minus 51.3. And so I actually get the angle at 129.7. So this would be square root of 41, 129, we'll just do 129 degrees, okay, just for rounding purposes. Okay, so I hope that makes sense there, but we just basically use some basic trig to find the angle. And then, you know, you're probably thinking, well, if we can go from one to the other, shouldn't we be able to do the other way? And that's true as well. So this one, again, is going to make us use some trig. So we're given the radius, we're given the angle. So the radius of 8 means that basically, that's not a good line there, means that this is a length of 8. It's basically got a hypotenuse of 8. And we know that the angle is pi over 3. If you want to rewrite that in degrees, that's fine too. So that's a 60 degree. Again, this is a special right triangle. It's a 60, 30, 90. And the ratio for that, in case you forget, is 2a, a on the short side, a root 3 on the long side here. So short here is 4, long is 4 root 3. So in terms of the standard x and y coordinates, it's just the other two side lengths of the triangle. Now let's say, for example, we have one that we don't know. Now we know the 45, but let's assume that we do not know it. So this is first off a negative angle. So we could add 180 here to create the positive radius. That gets me 225. So that's down here. Now, realistically, the 225 does not matter. If you build the triangle, use the 45 as your reference. But you definitely need the radius here. So with the 4, we know that this is a 45, 45, 90, but let's say we don't remember, and let's call this x and y, right? And so to get the x coordinate, if we think about the triangle as is, here's 4, here's the 45 degree, here's x, here's y. Let's say I find x first. If I remember my SOHCAHTOA, this is actually just the cosine value. So we can actually do this specific formula. The hypotenuse times cosine of the angle. So 4 times cosine of 225, since that's the actual rotated angle here. And we remember cosine of 225 from our unit circle is negative root 2 over 2, which simplifies to negative 2 root 2. Again, for a special right triangle, you may have already known that, and that's perfectly fine too. But when it's not an angle from the unit circle, we're going to have to use the trig components. And if I want to find the y coordinate now, y is opposite in hypotenuse, so now we can go hypotenuse times sine of the angle. So the y coordinate here is 4 times sine of 225, which is the same value, so we end up with negative 2 root 2. So this rectangular coordinate is negative 2 root 2, comma, negative 2 root 2. Okay, there's not one way to do this in a lot of the times, but that tends to be the most straightforward way. Even if you use the wrong angle at first, as long as you overcorrect it for the actual rotation, you should be fine. And so now this is where it's going to get a little bit more interesting. Now we actually have equations that we can work with. So polar and rectangular equations, because we just talked about how the radius or the hypotenuse relates to the x and the y coordinate, and we just talked about how tangent and r squared relate to the x and the y coordinate. We can actually draw equations and graphs in polar coordinates in the polar system, just like we spent all those years learning how to graph things like lines, parabolas, cubics, trig functions, exponentials, logs. All of these can be done similar to polar. Now I've got good news. We're not doing all those because they actually get extremely complicated, so we're actually starting with some pretty basic ones, and we're kind of leaving it like that. So here's how we might want to approach this. Just like in the last chapter, these are essentially identities in that we always kind of want to see these show up because it actually lets us look at the graph. Same thing this way. So if I'm in a polar equation, I kind of want to look and see if I can make these types of things happen. So let's look at our first example, in example 4. R equals 3 cosecant theta. So r equals 3. Now again, we're so used to not working with this, so let's go sine of theta. And we want to see r sine theta, so let's multiply both sides by r sine theta, or by sine theta. Sine theta over sine theta cancel. So I get r sine theta equals 3. And just like that, we're done because r sine theta is the y coordinate on these systems. So this is actually just the equation to graph the horizontal line at 3 in the polar system. Now this one you might look at and you think, we could do the same thing, divide both sides by cosine, and we get r cosine theta equals negative 6. And then we know that's secant, and there is no identity for r secant. So unfortunately, that's not the approach we want to take. What we want to look at is how else I can rewrite these things. And so one strategy that we have is actually to multiply both sides by r. So we get r squared equals negative 6 r cosine theta. And we know that's an x-coordinate. So r squared equals negative 6x. And at this point, I hope you're saying, but r squared is still in terms of r. I've now removed the polar coordinate piece in terms of the rectangular, but this is a problem until you realize that this formula exists. R squared equals x squared plus y squared. If you remember, that's the equation of a circle. We did this in chapter 1. So we can actually just move it here and then move the 6x to the other side. Equals 0. And if you remember, and we're going to do this a lot this chapter, we can complete the square to actually get the correct components of the circle. So if you remember completing the square, it's take b, divide it by 2, and then square it. So 6 divided by 2 is 3, add 9 here, add 9 here. And the reason is this is now factorable. This becomes x plus 3 squared plus y squared equals 9. So this is a circle with a center at -3, 0 and a radius at 3. I know for my friends that were doing some SAT stuff, recently we've looked at this again. You don't need to do it for this, right off the beginning part of the chapter. This is good to have for right now. But remembering this is going to be really helpful both this chapter and next chapter. And likewise, we can do the same thing here. Now, the good news is I actually think going from rectangular polar is a lot easier. So we just substitute these out for their r cosine, r sine counterpart pieces. So this would be r cosine theta plus 2r sine theta equals 1. And the goal, like we've had in linear terms, is always to get like y equals in terms of x. Well, it's always to get r by itself. So since this left side has a common factor of r, we can just factor it out and divide both sides by this 3 cosine theta plus 2 sine theta piece. And that's it. I mean, this is a linear equation. If you remember back in the Algebra 2 or Algebra 1 days, it would probably be something like that. This is the equation of the polar coordinates that would actually produce that. And finally, we have this. Now, again, this is all about knowing how to manipulate the equation of the circle. This circle here is centered at 1, 0. Radius is 1. So realistically, we want to expand this first term. So we get x squared minus 2x plus 1 plus y squared equals 1. And I'm going to basically get rid of the 1's, and I'm going to regroup the x squared and the y squared together. And the reason is because this becomes r squared, and x becomes r cosine theta. And you might be wondering, what do I do here? So what we actually do is we factor out the r, and we get two simultaneous equations to work through. The first one, like solving a regular equation, is just r equals 0. The second one is r minus 2 cosine theta equals 0. Now, this right equation is the only one that we can do something with. So this is the actual equation. This is just the center pole, which realistically in terms of graphing does not mean anything. So this equation is actually the representative of this entire rectangular system. And the last thing I want to show you in our notes for today is how we can use a lot of these pieces together to show multiple representations. So here's the coordinate point, h. We're going to plot at 3 2 pi thirds. So third radius circle, go up to 2 pi thirds. So right here is my coordinate. So that's coordinate h. And we just want to talk about how else we can represent it. So the first one is we want to form the same equation, the same coordinate, but point h, but has a negative radius this time. So I need to make 3 negative here. So we're going to go -3. But if you remember from the previous page, we can either add or subtract pi. Now, we normally want to keep our angle within the unit circle still. So if you add or subtract and you end up getting out of it, you should probably add or subtract 2 pi again ahead of time. So in this case, what I would do is I would add pi. So we get 5 pi over 3. And visually, if you look at your graph, here's 2 pi over 3. Directly across from it is the actual correct angle, 5 pi thirds. Now, we want to do point h with a negative angle this time, still keeping a positive radius. This is easy. So we just subtract 2 pi, because again, it's the same angle, but it keeps everything the same. So 3, if I subtract 2 pi, that ends up being negative 4 pi over 3. And finally, we want point H where the angle is greater than 2 pi. It doesn't specify whether or not we want a positive or a negative radius. So you could actually use either the coordinate from A or the initial, but I'm just going to add 2 pi to the initial, and we're going to satisfy the condition being asked, 8 pi over 3. So all of these are different ways to represent. Now, what makes this interesting is seeing as we have all these different ways already, that means every polar coordinate can be represented in infinite amount of ways. Rectangular coordinates have never been able to really do that. Each one of these angle rotations actually has that implication of having the same value but different rotation level, which is why we like this system, because it tells us more information embedded based on the angle given. All right, well, I hope that was helpful. Please feel free to go back through and rewatch this video if needed, and I'll see you in the next class. Try the practice problems that are in the problem set. Have a good night.